Have you ever looked through a window, held a glass bottle, or tapped on your smartphone screen and wondered, how on earth is this made? From skyscraper windows to windscreens, glass shapes our world in ways we barely notice. But behind every sheet, bottle, and fiber lies a hidden journey, an industrial alchemy of fire, chemistry, and precision. Today, we'll be uncovering the fascinating journey of glass, from ordinary sand to the crystal clear material we use every single day. In this video, I'll take you inside the factory and break it down into 7 simple steps. From melting raw materials at blazing temperatures, to shaping, cooling, and polishing, you'll see exactly how industries transform sand into one of the most useful materials on the planet. So stick around, because by the end, you'll never look at glass the same way again. First stage is raw material preparation batching. Manufacturing starts with carefully measured blending of raw materials. Silica sand, soda ash, limestone, dolomite, and sometimes cullet, recycled glass to form the main components. Additional additives may include feldspar, salt cake, and colorants depending on the glass type. These ingredients are finely ground and thoroughly mixed to ensure homogeneity. What's the purpose? To deliver a clean, precisely proportioned, free-flowing mix that will melt and refine predictably in the furnace every hour of every day. What's in the batch? Soda lime glass, the most common industrial glass. Silica sand, the network former, approximately 74% of the final glass. Soda ash, flux that lowers sand's melting point, provides approximately 16%. Limestone and dolomite stabilizes, adding for durability. Minor oxides are a bit of feldspar or clays for chemical resistance, and then tiny amounts of colorants or decolorizers such as iron, cobalt and selenium to tune color, and sulfate, often sodium sulfate, to aid fining later. Cullet recycled glass is a big lever. It melts far easier than raw minerals, so it cuts energy use by approximately 3% for every plus 10% cullet. Flat flow glass usually runs lower cullet shares than containers, often E40% due to tight optical requirements and cullet availability. Containers can run 50 to 90% when supplying cullet allow. Benefits also include higher pull and lower particular carryover. Cleanliness matters. Non-glass contaminants such as ceramics, stone, porcelain, CSP, metals, and organics create stones, bubbles. How the batch house works. Typical features. Receiving and storage. Silos or hoppers with level sensors hold sand, soda ash, limestone and dolomite, cullet, fines, and additives. Dosing and weighing. Loss in weight or weigh hopper systems meter each ingredient onto a common conveyor to the mixer with tight tolerances. Mixing. Usually dry mix is firstly done, then a small water addition to control dust and improve flowability and adhesion, so the batch blanket feeds evenly at the furnace doghouse. Dust and safety. Enclosures and dust collection protect workers and reduce raw meal losses. Silica dust control is a major design driver. Optional preheating. Many modern plants preheat batch or cullet with furnace exhaust, routinely saving approximately 10–15% melting energy. This can also raise line capacity. Consistent sizing. Moisture and chemistry minimize foaming and gas release spikes in the melter, reduce seeds, and makes the second stage faster, cleaner, and cheaper. Second stage is melting and refining, turning batch into a clear, homogeneous melt. The batch is fully dissolved. Drive off gases, typically carbon dioxide and fining gases, eliminate bubbles, even out composition/temperature, and deliver glass at the right viscosity and temperature to the forming stage. Furnace and firing basics. Large regenerative, cross-fired, or end-fired tanks are standard for fat/container glass. Float furnaces are the biggest, typically approximately 600–800 tons per day, range approximately 250–1,200 tons per day. Plants often add electric boosting, immersed electrodes, or supplemental oxy-fuel to improve melt quality and capacity. The temperatures is soda lime batch, and it is melted at roughly 1,550 to 1,600 degrees Celsius. The glass then conditions down to approximately 1,200 degrees C before forming into the float bath. What actually happens in the glass? Melting reactions. Carbonates decompose, releasing COO. Grains dissolve, and the network forms. Cullet accelerates these kinetics. This is the most energy-intensive part of the whole plant. Refining. Tiny bubbles must be removed. A traditional aid is sodium sulfate. At high temperature, it releases sulfur dioxide or oxygen, which first grow bubbles, so they coalesce and rise faster. Then, as the melt cools, gas solubility increases and bubbles shrink or dissolve out. Plants tune redox with small oxidizers or reducers such as nitrates and carbon to make fining efficient without discoloring the glass. Homogenization. Natural convection helps, but modern furnaces often use electric boosting about 5 to 20% of total heat in some setups and bubblers, or styrers to even temperatures in composition, shorten refining times, and cut defects. Quality risks and controls. Seeds from incomplete refining, unmelted contaminants, and compositional streaks are classic defects. Prevention =, clean cullet, controlled furnace chemistry and temperatures, good refractory choices, and adequate conditioning time. Energy and emissions context. Melting or refining dominate energy demand and CO. CO big levers are more clean. Cullet preheating, electric boosting melters, and cleaner fuels. A good example is hydrogen trials on float lines. Coming to the third stage, forming and shaping. This is how molten glass becomes bottles, jars, and as many as you can mention. There are various shaping techniques depending on the desired final product. A. Two very different worlds, flat or float vis-a container glass. The forming step diverges depending on product. Flat glass produces windows, automotive glass, and flat sheet glass. The melt is floated on a tin bath and becomes a continuous ribbon with two optically smooth faces. Container glass produces bottles, jars, and hollowware. Molten gobs are metered, sheared, and formed. Float glass forming, the tin bath, and ribbon control. Tin bath fundamentals. Molten glass is delivered from the furnace onto a bath of molten tin. Because tin is denser than glass and has suitable vapor/boiling characteristics at operating temperatures, the glass literally floats and spreads into a perfectly flat ribbon. The tin surface must be protected from oxidation by an inert positive pressure atmosphere, commonly nitrogen with a small hydrogen content. Otherwise, tin forms tin oxide that contaminates the glass surface and the tin bath. Ribbon formation and thickness control. The molten sheet initially spreads to an equilibrium thickness determined by mass flow and surface tension forces. Operators control final thickness by adjusting the flow rate of glass onto the bath and the pulling speed of the ribbon rollers, and sometimes with top rollers. As the ribbon travels, the top and bottom surfaces self-level to produce mirror smooth faces. Atmosphere and dross management. The tin bath's protective gas prevents tin oxidation. Dross still forms and must be skimmed or otherwise managed. Accumulated dross and contamination can cause surface defects that are costly to remove. Bath chemistry and maintenance are essential for quality. Thermal profile and transfer to the cold end. While in the bath, the glass is held at very high temperatures on the hot end at a temperature of approximately 1100 degrees C, while entering the bath and gradually cooled. It is usually reduced to roughly approximately 600 degrees C at the point where it is lifted off the tin onto rollers. From there, it enters the annealing layer. Cooling rate across the tin bath and transfer to rollers must be controlled to avoid distortion and internal stress. Common flow control points: post-tin operations, edge trimming, cutting, wash. After the layer and cold end, float glass is cut, edged, washed, and inspected. Cutting is done by scoring and snapping or CNC cutters for precision. Edges are ground and polished where required. Automated inspection cameras check optical quality and dimensions. Watch how the molten river spreads like mercury on a hot metal mirror. That metal is tin, and the miracle it performs is why modern windows are perfectly flat. Seek container glass forming, gob feeding to finished bottle. Gob formation and delivery. A gob feeder or feeder former meters a stream of molten glass from the furnace and shapes individual gobs like discrete drops through an orifice. The mechanical shear cuts the gob. The timing and gob mass are tightly controlled because weight affects wall distribution and strength. The individual section machine, how a bottle is born. The most common high-speed configuration is the IS machine, which has multiple identical sections operating in parallel. Each section receives a gob and performs a sequence blank forming and final blow. In a blow-and-blow sequence, the parison is formed by a blow, then transferred and blown again into the final mold. In press and blow, a plunger presses the parison to form the finish and improve glass distribution, then final blow shapes the body. NNPB is a special press and blow variant for narrow neck containers like narrow mouth bottles, giving superior distribution and speed. Molds, neck finishing, and takeout. Parison and final molds are water-cooled tool steel pieces that dictate shape and texture. Neck finishing and reheating steps may be used so that the finished threads, lips meets dimensional tolerances. After forming, automated grippers take the hot containers to the lair for annealing. Some high-end lines include hot end coatings so as to improve abrasion resistance before the lair. Typical control signals and cycle times. Modern IS machines are heavily automated. Gob detection, blower timing, plunger position, mold temperature, and parison weight are monitored and adjusted in real time. Cycle times and throughput vary by machine, but high-speed IS lines can produce hundreds of items per minute across all sections combined. Quality is highly dependent on consistent gob weight and precise timing. Typical container defects and root causes. Common container defects such as poor distribution due to thin walls or heavy heels, seams or parting line defects, stones, bubbles, wrinkles, and dimensional failures. Causes range from incorrect gob weight, dirty or overheated molds, improper takeout timing, to contaminants in the batch. Every bottle starts as a precisely timed gob of glass missed the weight by a gram, and you change the bottle. Automation, sensors and quality control during forming. Lines use optical thickness gauges, pyrometers, cameras, and machine vision to measure thickness, temperature, and surface defects in real time. Rock-solid feedback loops between feeder, forming machine, and conditioning areas maximize yield and minimize scrap. For containers, automated reject systems and defect logging enable fast root cause analysis. At stage 4, annealing and stress relief, the lair, theory, and practice. Why annealing is absolutely critical, the theory in plain terms. During forming, the glass has temperature gradients and frozen-in stresses. If cooled too quickly, tensile stresses remain and can cause delayed or spontaneous fracture under small loads or temperature changes. Annealing slowly relaxes those stresses by holding the glass around the annealing point, where viscosity poise, and then cooling at controlled rate through the strain point into room temperature. Proper annealing is the difference between reliable glass and a failure risk. The lair, design, zones, and profile. Flat and container layers. Flat glass layer, which is also called float cold end. After the tin bath, the float ribbon passes through a very long annealing layer. It can be 100 to 200 meters or more, where the glass is cooled from roughly approximately 600 degree down to approximately 60 degree in carefully controlled stages. The layer's length, zone temperatures, and conveyor speed are tuned to the glass thickness and composition. This long cooling path relieves stresses without causing distortion. Container layer. Formed containers enter a container layer, where they are heated or held briefly to remove thermal gradients, of which some designs reheat slightly at the layer entrance, and then cooled at a controlled rate. The layer profile is tuned by container mass, geometry, and thickness distribution to ensure outer, and inner surfaces pass through the strain at annealing ranges with minimal residual stress. Typical profiles and control parameters. Annealing requires set points for soak temperature, that is near annealing point, cooling ramps, conveyor time, which is measured in seconds to minutes depending on the product, and final cool down. These values are calculated from glass composition, soda lime against borosilicate, and product geometry. Engineering texts and plant recipes define exact curves. Tools like finite element thermal modeling and empirical tuning are used. Let's dive into steps 5, 6, and 7 of industrial glassmaking. At stage 5, surface treatments and post-processing. Forming is where molten glass takes on its final shape. Depending on the product, factories use very different techniques. Float glass. In float glass production, continuous ribbon of molten glass is poured onto a bath of molten tin. Because glass floats on tin like oil on water, it spreads out into a perfectly flat sheet. Rollers gently control thickness, while the ribbon moves forward at a steady pace, smooth, flawless and ready for cutting. Container glass. For bottles and jars, factories use automated forming machines. Here, precise gobs of molten glass drop into metal molds. Using compressed air, the gobs are blown or pressed into their final shape. In just seconds, glowing blobs transform into bottles, ready for cooling. Fiberglass. For fibers, molten glass passes through platinum bushings, plates drilled with hundreds of fine holes. As the glass exits, it's pulled into hair-thin strands, cooled by air or water, and collected onto spools. This lightweight yet strong material is used in insulation, composites, and even high-performance applications. Moving to stage 6, quality control. Freshly formed glass may look solid, but inside it's full of internal stresses from rapid cooling. Left unchecked, these stresses could cause the glass to crack or even shatter. That's where annealing comes in. In the annealing process, glass products enter a long temperature-controlled tunnel called a layer. Inside, the glass is reheated to just below its softening point, then cooled down very gradually. This controlled cooling relieves stress and ensures the glass is stable, durable, and safe to use. Finishing in stage 7, cutting, packaging, and distribution. Finally, every piece of glass must be inspected before it's shipped. Quality control ensures that only flawless products make it to customers. Modern inspection combines human eyes with high-tech sensors. For flat glass, lasers and cameras scan for scratches, bubbles, or distortions. For bottles, vision systems check dimensions, wall thickness, and even stress patterns using polarized light. Even the smallest defects can cause rejection. Rejected glass isn't wasted. It's returned to the color stream and recycled back into the furnace, ensuring efficiency and sustainability. So, through shaping, annealing, and inspection, molten glass transforms into safe, reliable products we use every day. But the story doesn't end here. Next comes finishing, packaging, and the incredible journey glass takes to our homes and industries. From raw sand to shining glass, we've witnessed how fire, chemistry, and precision engineering reshape the earth itself. Every bottle, every window, every screen carries this hidden story of transformation. Glass is more than just a material, it's a bridge between nature and technology, an ancient art refined for the future. So the next time you look through a window or raise a glass, remember the incredible journey behind it. And if you enjoyed uncovering this process, hit the subscribe button, give this video a like, and turn on notification bells for more, and stay up as we explore more hidden worlds of how things are made.